morning. Today we will study real numbers, chapter 1 of class 10. And before starting this chapter, we will go through some basic concept of number system. Let's start. This is a whole chart of number system. First you must have studied what are natural numbers. Natural numbers are numbers denoted by n and they start from 1 to infinity like 1, 2, 3, 4, 5, 6, 7, 8. All these are natural numbers. If I want I can write it over here also. Natural numbers will be from 1, 2, 3, 4, go on till infinity. These are natural numbers. Next, when we add 0 to a natural number, it becomes whole number. Whole number is denoted by W and they are like starting it from 0, 1, 2, 3, 4 up to again infinity. This is also up to infinity. Positive infinity. Both are positive infinity. So natural numbers, when we add 0 to it, it becomes whole number. That means natural number is a part of whole number. Next, while coming to integers, as whole numbers are just positive numbers starting from 0, what about the negative numbers? If we add negative numbers to a whole number, it becomes integer and we denote it by Z. So we can say those numbers are like this, the one written over here. These are integers. Now, when we add fractions, now we have what we have? We have positive numbers, we have negative numbers and 0 altogether becomes integers. Integers are the two type, positive integers, negative. Positive integers are basically whole numbers. Adding negative to it becomes an integer and all. What about fractions? You have also studied the fractions also. When we add fraction to an integer, it becomes rational number. When we add fractions to an integer, it becomes rational number. And rational number are in the form of p by q. They are in a form of p by q, like p by q, where q is never equals to 0 as stated over here. Now, is there a number which can be written in integers can be written in rational form? Yes, you can easily write an integer in rational form. Like there is a number called 2. Now this is integer, but if I write it like 2 by 1, this will be called rational numbers. So any number can be, we can write in rational forms. So any number I mean to say up to integers, not irrational numbers. We will study the irrational numbers also. Now, what about those numbers which cannot be further written in p by q form, and they are basically non-terminating decimal numbers. They are called irrational numbers, like this. Basically, irrational numbers are non-terminating decimal numbers, like under root 2, under root 3, under root 5, pi. All of them will have a value of non-terminating decimal numbers. Now, next. When we add these type of numbers to a rational number, we got a number from p by q. P by q, whenever we write p by q, the number will be either terminating decimal or non-terminating repeating decimal number. Whenever we will write a rational number, it will be either decimal terminating number or a integer or a non-terminating recurring decimal number. We will study all three of them also. And rational numbers are those which the result of which will be non-terminating, non-recurring decimal numbers. It will be denoted by q. Rational numbers are also denoted by q, and irrational is also we can write it q dash. When we add rational and irrational, means all of them together are called real numbers. Real numbers have all such kind of numbers, whether they are positive, negative, zero, fraction. You can say those fraction and integers become rational numbers or irrational. In irrational, whether they are we can say whether they are decimal, non-decimal numbers, decimal reoccurring, non-decimal numbers, then decimal numbers, non-reoccurring, non-terminating, decimal number, terminating, decimal number, non-terminating. These all type of numbers are a part of real number system. Now again, a few small questions which comes are like, is a natural number is a part of all number? Yes, it is a part of all number. Is all whole numbers are natural number? No, because in whole number there is a zero, where in natural number there isn't any zero. Is a whole number, all whole numbers are integer? Yes, all whole numbers are integer. But is an integer a whole number? No. These small type of questions can come in objective questions. Is integer a rational number? Yes, it is a part of rational numbers because rational number has all integers. Is all rational numbers are integer? No, it is not. Why? Because fractions are not a part of integers. Same way for real numbers and others. Now we'll move to next part. First theorem of chapter 1, that is Euclid division lemma. The theorem states that given positive integer a and b, there exists a unique integer q and r satisfying a equals to bq plus r, where r is greater than or equal to 0 or less than b. Now we will actually study this theorem. Let's say we have a number, this is a theorem. Given positive integer a and b, there exists a unique integer q and r satisfying a equals to bq bar. Now, getting back to this, we will, as we know, there is a you must have studied a remainder theorem, or basically you have studied the division way, how we divide. Let's see over here. Division term and the relation. When we divide a number, the number we divide becomes a dividend. The number which is divided by another number, the number by which we are dividing, becomes a divisor. The quotient is what is over here, and the remainder which remains. And the theorem states that dividend equals to divisor into quotient plus remainder. This is basically the same as A, which Euclid's division lemma states A equals to B Q plus R. Let's start from here. Let's say we are dividing 30 by 8. Then as we are dividing 30, it will become a dividend. The 8 will become the divisor. 8 3s are 24. This 3 will become the quotient, and 6 as it is remaining becomes the remainder. Now the theorem states that, as the theorem states, that dividend is equals to divisor into quotient plus remainder. This is the same, and this is what Euclid tried to explain with its theorem, that A equals to BQ plus R, which you can state that A equals to, what is A over here? You can state that A equals to dividend, B equals to divisor, Q equals to quotient, and R is the remainder. He further stated that R will always be greater than equals to 0, because R can always be greater than equals to 0, because as you know, remainder either comes to be 0 or any positive integer, but it never comes to be a negative integer. So it will be either equals to 0 or greater than that, or less than b, means less than a divisor. Even if it becomes equals to divisor, it can be further divided by a divisor by 1, as 1 into divisor will be that r. So this is what we get to know. Euclid division lemma states that A equals to BQ plus R, which is equals to dividend equals to divisor into quotient plus remainder. Now, further we will try to understand what this theorem actually states, or will help you to study in this chapter. Now let's see how this theorem works. So this theorem works to find HCF also. The theorem says that A equals to BQ plus R, where R is greater than equals to 0 and less than B. Now how we can find HCF out of this? First, try to understand what this division actually works on. If we had something in a portion and we are dividing it into parts, let's say I want this much part each to be divided in this. So I'll make this much part of same size and I'll try to cut. There is a small portion left. Let's say this is the portion left out of this. After cutting this, this portion left it. So now I have to satisfy this portion with this. First, I will try to satisfy it with this. Okay, maybe this portion cuts this all. Further, this much is left. Then I will try to cut this one with this. So finally I will get something by which this whole can be cutted, this whole can be divided. So similarly over here, I'll show a video also, a smart video for this to understand better. Let's see how we can find the HCF effect out of this. Let's say there are two numbers. We may write 42, comma, we say 13. There are two numbers 42 and 13, and you have to find the LCM between them. So let's say we are dividing these numbers according to the reset. What it will be? 42 will be the dividend and this will be the divisor. So we can write divisor as 13. Q will be the quotient by which we should divide this. If I write it like this, 42 divided by 13. 13 into 2 gives you 26. 13 into 3 gives you 39. 13 into 4 will gives you 52. 52 is greater than 42, so what will be the answer? 13 into 3 gives you 39, and remainder will be 3. And remainder will be 3. So over here we will write 13 into 3 gives you a remainder 3. Now this 3 is the portion which is left over here. So we will try to satisfy this 3 with this. If it cuts this completely, that means that will be the answer. 13 equals to 3 is the remainder. 3 into 4 we know is 12 plus 1. Only 1 is left. Now this one is this portion, small portion which is left. Now we will try to satisfy this whole with this small portion. Again we tried it and we got 3 equals to 1 into 3 gives you remainder 0. That means this 1, this small unit can satisfy both, and 1 is the smallest unit for anyone. It is the only HCF which is in between all the numbers. Even prime number has a common factor, that is 1. So this is the common factor between all. So HCF for this is 1. HCF for this is 1, as 13 is a prime number. This is also you can say. Now let's go to a video which will help you to understand it better.
How we can calculate the HCF of two numbers with the help of Euclid's division algorithm. Over here I have two numbers A and B where A is greater than B. So first of all, what do I need to do? I will first check whether B is a factor of A. If B will be a factor of A, then my HCF will be B itself. For that, I need to check if B can completely divide A. So what will I do? I will try to take out B units blocks from A. So this is my first block, but I can see that there is a lot of space left. So I can take out one more B units block from here. But I can see that there is still some space left. So what will I try to do? I will try to take out one more B units block. But I can see that that's not possible because we don't have sufficient space. This means that B cannot be a factor of A, and hence we get some remainder. Let's say that is C. So now what do we need to do? We need to find out a number that is smaller than B, that can completely divide B also, and that can completely divide A also. If a number completely divides B, then obviously it will completely divide A till here. But if it has to completely divide A, then it needs to divide the leftover part of A as well, that is C. This means now what I am trying to do, I am trying to find out the highest common factor of B and C. If I need to find out the highest common factor of B and C, I need to divide B by C now. That means I need to take out C units blocks from B. Now this is my first block, but I can see that there is still some space left. If I try to take out one more C unit block from here, I'll see that it's not possible, and it is also leaving out some remainder. Let's say that this remainder is D. Now I can conclude that definitely C cannot be a factor of B. And now what do I need to do? I need to find out an even smaller number that can completely divide C also, and that can completely divide B also. Now again, if a number can completely divide C, it can definitely divide B till here, but it also has to divide this leftover part of B, that is D. So that means now I will try to find out the highest common factor of C and D. In order to do that, I'll have to divide C by D. If I do that, I see that D can completely divide C. That is, I can obtain D unit blocks from C, and this D is the highest common factor of A and B, and we can easily see that. Now you can clearly see how D is the highest common factor of A, B and C as well.
Now let's study the first example of your NCERT book, that is over here. Show that every positive even integer is in the form of 2q, and that every positive odd integer is of the form 2q plus 1, where q is some integer. Let's see how we can solve this. So what it is asking you to prove that every positive number can be written in the form of 2q. So let's say using Euclid's division lemma we will show that. So what it states, Euclid's division lemma states that a is any number which when divided by b gives you a quotient q and remainder remains as r. If it is completely divisible by b, then the remainder will be 0. Okay. Now we will take let a be any integer. Now a is any integer, could be any number that we are taking a positive integer basically. And b will be equals to 2 because first we are checking it for even integers. B could be 2 if we are dividing it with 2. That means it is an even number. This is the number a and we are dividing it by 2. So we can write a as dividend and b as divisor. Now the Euclid division algorithm will become a equals to 2q quotient plus r, and r will be greater than equals to 0 and less than 2 because it is less than b. The value of r could be 0 and 1. There could be only two possible values of this number. Then the equation on putting r equals to 0, we get a equals to 2q, and putting r equals to 1, we get a equals to 2q plus 1. As we know, this is completely divisible by 2. If a equals to 2q means a is a positive integer, is a positive even integer. Whereas when we do it 2q plus 1, then 2q makes it even, any integer. Q could be any integer 0, 1, 2, 3, 4, 5, 6. Let's say we take q as even number. Let's say we take q as 2. 2 into 2 is 4. Over here this number will be even. Now over here 2 into 2 is 4 plus 1 5. This will become odd. Now let's take q as an odd number. Q is 3. 3 into 2 is again 6 even. 3 into 2 6 plus 1 odd. So whatever number we will take q, it will either be an even number, in this case it will always be an even number in this case, an odd number in this case. So hence we can show this out that every positive integer is even integers in the form of 2q. Yes, it is in the form of 2q. And every positive odd integer is in the form of 2q plus 1. You must have studied this before also. Like when in questions you are asked to write 3 consecutive even numbers. So how you start writing it? You write it 2x, 2x plus 1, 2x plus 2 and 2x plus 3. This will be your 3 positive even numbers, consecutive even numbers. And how you are asked to write odd numbers, 3 consecutive odd numbers? You write it like 2x plus 1 and 2x plus 3 as 2x plus 4. This starts with 2x plus 1, this starts with 2x. Any positive even number is always in the form of 2q, where q could be any positive integer, or every positive odd integer is in the form of 2q plus 1, where q is also again any positive integer. Now let's go through some questions of exercise 1.1. The first question is, use Euclid division algorithm and find the HCF of 135 and 225. Find HCF. We have to find. So how we will start this out? Let's see. We have to find the HCF of 135 and 225. So using the Euclid division algorithm, we know that A equals to BQ plus R. So let's start it over here. This is a bigger number, so this we will take as Dividend, it will become 225 equals to 135. Now 125 into 2 will gives you 135 into 2 will be a number greater than 225. It will be, any guess? If I multiply 135 into 2, the number will be 270, which is greater than 225. So this can only be multiplied with 1, and the remaining will be 225 minus 135 gives you 90. Now next, these two numbers we need to cross check. This is a bigger part and this is a shorter part. If this satisfies this, then this will be the remainder. This will be the HCF. But let's check it out. 135 equals to 90. 90 into 2 equals to 180, which is again greater than 135. So it will also go with 1. Gives you a remainder 45. I'll check these two. 90 will be equals to 45 into 2 equals to 90, and remainder is 0. As 45 satisfies 90, 90 will satisfy 135 with 1, and 90 and 135 satisfies 225 with 45 is that number which can satisfy all of them and both the numbers 225 and 35. 45 will be your HCF. This is how you can find HCF of any two numbers using this algorithm. Now next question, let's see. Next question is, show that any positive odd integer is of the form 6 cube plus 1 or 6 cube plus 3 or 6 cube plus 5 where q is some integer. Now as this is your question number 2, how we can solve this out? Again using Euclid algorithm, we have to find that all positive odd integers is in the form of 6 cube plus 1. If I write it like this, a equals to b cube plus r, over here I have to show that it is 6 cube plus 1, 6 cube plus 3, 6 cube plus 5, means a should be divisible by 6. A should be divisible by 6. We have to divide a by 6 basically. So what we will say first what we will do is say let a be any positive integer. A be any positive integer and b will be equals to 6, because we have to divide it by 6 so that we can find out the result. Over here we are taking 6 with q. Therefore, Euclid division algorithm will be a equals to 6q plus r, where r will be greater than equals to 0 and less than 6. The value of r will be equals to 0, 1, 2, 3, 4 and 5. These will be the value. Now we will try to satisfy this value in this equation. First one will be a equals to 6q when r equals to 0. Second, a equals to 6q plus 1 when r equals to 1. Similarly, third one, a equals to 6q plus 2 and a equals to 6q plus 3 and a equals to 6q plus 4 and last a equals to 6q plus 5. Over here r is 0, r is 1, r is 2, r is 3, 4 and 5. Now we have to find that, show that any positive odd integers in the form of this. We just need to find the odd integers. This will be always positive even number because it is divisible by 2. Now this will be odd. Why? Because there isn't any common factor between 1 and 6 except 1. You cannot take anything common, so this will be odd. This is not divisible by 2. Over here, what we can take 2 out common and it will be 3q plus 1. Now this 2 can be divided by 2. Therefore this again becomes a odd. So this becomes a even integer. Over here we can take out 3 common and it becomes 2q plus 1. Now this 3 cannot be is not divisible by 2. Therefore this will be a odd number. Then we'll check this. Over here we can find take 2 common, it will be 3q plus 2. Again this can be divided by 2. If it is even. And last over here there isn't any common factor, it will remain as 6q plus 5 and it is not divisible by 2, therefore it is an odd number. So we have 3 odd numbers, that is, first is this one, second is this one, and third is this one. So this proves that any positive odd integer is to the form of 6q plus 1, 6q plus 3, 6q plus 5, which we have to prove over here. So yes, our proof is correct. Now coming to question number 3, an army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? Now the columns should be same. That means there should be some common factor between both two groups. And to find that common factor, we have to find HCF between both two groups. So we will find the HCF of 616 and 32. This you can do yourself. Now next, coming to question number 4, that is Euclid division lemma to show that the square of any two positive integers is either of the form 3m or 3m plus 1 for some integer m. Now let's start doing this. As we know that we have to show that square of any positive integer is in this form, and the number which we have to show is 3m or 3m plus 1. Again we have to show that it is divisible by 3. The a which we'll take, let a be any positive integer and b equals to 3, because we have to show that it is divisible, this integer is divisible by 3. Now what we will do, we'll write an algorithm. The Euclid algorithm will be a equals to bq plus r, where a is a and b is 3q plus r, where r is greater than or equals to 0 and less than 3. And the value of r will be 0, 1 and 2. Now put these values. On putting these values we will get, first equation will be a equals to 3q when r equals to 0. Second equation will be, writing it over here, a equals to 3q plus 1, and third will be a equals to 3q plus 2. These will be 3 equations. Now we have to square this. Over there in the question it is written, use the Euclid division lemma to show that the square of any positive integer. This is a positive integer. The values are this. If we square them out, let's say we'll square this one, it becomes a square, square both the sides. If we square this one, it becomes a square equals to 3q whole square, where a square will be equals to 9q square. We can take 3 common from this, it becomes a square equals to 3 into 3q square. We can take this 3q as m, because over there it is written for some integer m, and m is any positive integer. It could be any positive integer, any integer. If m is an integer, therefore we can take 3q square equals to m, because this will be an integer only and we can show it in by m as it is written in the question. Therefore a square will be equals to 3m. This is a proof of our first statement, that any positive square of any positive integer can be written in the form of 3m. Now second over here, let's see, squaring this one will get we get a square equals to 3q plus 1 whole square, that is a square equals to 3q whole square, means a plus b whole square is a square plus 2ab, that is 6q plus b square, that is 1. This can be written as 9q square plus 6q plus 1. From this we can take out 3 common from this one, and it becomes 3 equals to 3q square plus 2q plus 1. Now this 3q square plus 2q can be written as m, because again m is any integer, and this will also gives you a integer. We are neither in fraction nor in under root, but it will always be a integer. Therefore we can say 3q square plus 2q equals to m, and a square equals to 3m plus 1. Hence second statement is also proved. Therefore any square of any positive integer is either in the form of 3m and 3m plus 1. Now after this there is another question, that is use Euclid division lemma to show that cube of any positive integer is in the form of 9m plus 1 and 9m plus 8. Now in this one you don't need to do anything new. You just take this, you just carry over from this question, so the above question only. We have formed the equation like this. The equation was 3a equals to 3q plus r, where r is less than equals to this. So we can write it in this form. There were 3 equations. First equation was a equals to 3q. Second equation was a equals to 3q plus 1, and third was a equals to 3q plus 2. Over there we have in the above question we have squared each equation. In this one we will find the cube of these equations. On cubing a cube plus 3q cube, we'll get a cube equals to 27q cube, out of which we can take 9 common, and 3q cube will be taken as m, because m is any positive integer. So this completes your exercise. I hope this will help you to understand it better. Stay home, stay safe. Thank you.